Hello, thank you for coming to the Society for Conservation GIS virtual conference. My name is John Gallo. I'm presenting today the latest version of our software for prioritizing climate-wise habitat linkages. The version has been updated as of 7 days ago and is a very stable beta version available for download. What I'm going to do is give a brief overview of the software itself. Then I'm going to get into details about the science of connectivity, especially when it comes to incorporating climate concerns. There are two dominant theories out there about how to do this best. One is known as range shift climate gradients, and another is climate analogs. And the theory we're presenting today shows that both of these are actually same components of an overarching equation. And we've programmed that equation into the software so that you can apply one or the other or both. I'll give an overview of what that looks like with some sample data, and then briefly identify a few opportunities for you to engage. Now, starting with the big picture, there are many different strategies for conservation of biodiversity. One key strategy is spatial conservation prioritization, which is looking at the entire landscape and prioritizing where we should invest our scarce resources. An important criteria of all this is connectivity and how habitats connect to each other, how species move within these habitats. And this is especially important for maintaining genetic diversity and the maintenance of biodiversity itself. One way of mapping connectivity, this was done about a decade ago, is to identify the areas that you want to connect and then identify how they can be linked together. And so in this case, it was expert knowledge that determined which of these core areas to go ahead and connect. And each one of these particular linkages was processed individually and manually. And so we've come a long way since then, and one of the great ways of doing this is with the Linkage Mapper Toolbox, which allows you to do batch processing for all the linkages on a landscape. It uses the same least cost corridor theory, but it's done with Python script tools in ArcGIS, and it's an open source project. And so one of the ways to do that, just to break it down a little bit briefly, is here's a sample landscape of the Central Valley in California with the core areas in green and a resistant surface underneath, so the areas in darker red are higher resistance. And so with that, you can create the least cost corridors output, with one click of the button, mapping all these linkages. There's certain threshold parameters you can set in there for which linkages are too far to map. But then the question becomes, so this is where the state of the science was about 9 years ago. Then the question becomes, well, which of these linkages are most important and which should not be mapped at all? And the linkage priority tool, which is a fairly new addition to the linkage mapper tool set, helps with that. It's a systematic way of putting a whole bunch of priority criteria of the linkage into the analysis and combining them in weighted sums. Things such as the mean permeability of a linkage. So you can see down here, this linkage between these two core areas has to go through a lot of really high resistance habitat. So that linkage is not going to be as high of a quality as some of these other ones that go between areas where there's a lot of green. And the centrality of the linkage in the region, things like climate gradients, which we'll talk about more, and the importance of the two cores being connected, and 7 other criteria, which I'll get into more at the lunch workshop today. And so what it does, the linkage priority tool, the raw product, is it really applies values in a table about linkage priority to the linkages themselves. And then what you can do is you can then combine that with the linkage pathways in a weighted sum so that you get kind of a combination of both of those products, identifying the linkages, the importance of where in a linkage the most important paths are and which linkages are most important. And you can set the weights of that sum. You can also automatically remove the low quality linkages. You can also then combine the calculations with pinch point mapper. Pinch point mapper is here on the left. It uses circuit theory. It calls circuitscape and identifies the pinch points on the landscape. So you can add that into that previous thing, creating even more detailed of a mashup. And so we have a new tool that helps with that combination. And then one of the tools that's been getting a lot of interest lately is the idea of prioritizing the restoration areas on the landscape based on restoring the linkages. And so barrier mapper helps with that. And so here's an overlay of that previous, in a different landscape of that previous layer. So what is improved with Linkage Mapper version 3.0 beta? Well, we've taken the climate analog value component and really fleshed that out in a lot of detail, bringing together two different theories that are in the literature into one formula. And then while I have this slide up here, I'll also point out that there are these two wildcard boxes that allow the end user to also gather additional data on the landscape and throw that in. And so there's been a lot of talk about looking at identifying the relative threat to the linkages and adding that, so that can be done this way, as well as identifying where the human-wildlife conflict zones are and adding that as a criteria to helping determine your relative priority in a systematic way. Similarly, you can look at that for the core area value if you have information about population numbers for a focal species and things like that, that can go in there. So let's jump into here things with the climate analysis. So as we know, with climate change, suitable climates are moving, and here's just a schematic of a landscape. This is that same Central Valley looking north in California. That's Lake Tahoe on the right, and so you have that this gradient of going from the low valley floor all the way up to the high mountain peaks. And so in that situation, imagine three different cores, core A, B, and C, that are really wild areas that you want to connect. And so one option is a linkage between A and B. Another option is a linkage between A and C. Well, with climate change, the suitable climate in A and B 100 years from now might not be suitable anymore for a wide swath of species. And so investing a whole bunch of time and energy over the next 100 years and maintaining that linkage between the two might be a relative waste of resources. So in this case, the choice is clear that if you had to choose between investing in conserving these two linkages, you'd want to do it between A and C. However, it gets more complicated when you look at this issue of range shift connectivity, which is between A and C, versus climate analog, A and D. A climate analog is that, in this case, it's the assumption that with climate change, the current climate in area A is going to move upslope, and say some time period in the future, say 50 years from now, that climate is going to be where area D is. And so those two are climate analogs. Range shift connectivity is just knowing that eventually over the foreseeable future, things are going to need to move upslope. And so maintaining the linkage between A and C is a good idea, especially if the linkage is wide enough that the species can have home range within it. So here's a landscape of demo data. Notice the high mountain peak on the right, and on the left, the low valley floor in the middle. And so if you go ahead and map climate characteristics underneath those, here it is looking from the top, those same areas in more detail. And this is climatic water deficit. In this analysis, you want to use some sort of climate metric that's a single value that includes temperature and precipitation. And so in this case, it ranges from a value of 7 to 820 on the landscape. You can take the mean value of each one of these core areas to get their climate signature, ranging from 329 to 661. And you can also look at that in the future climate. Here it is 50 years in the future. You can see the climate signatures have increased. So you can combine, look at those side by side, looking at the current climate with the black text, future climate with the white text, and the core numbers with purple. And you can say, okay, now we got our linkages. Which ones are the most important for climate connectivity? And so in version 3.0, we've realized that both of those are actually two aspects of the same formula. Especially if you look at this idea of the climate analog ratio, which is the climate signature of the destination core at future time t over the climate signature of the starting core at the current time. And so the climate analog approach is that you want R values closest to 1, and range shift connectivity approach is that you want the lowest values of R on the landscape, and those are the best. And so that's simply represented here. And so you can put that on a graph, and here on this sample landscape where the lowest R value on the landscape is a 0.75 and the highest is a 1.75, or actually a 1.25, that's a typo. And the best priority value is where R is equal to 1. So this is the climate analog formula that's used in the literature and implemented in various other case studies. And then the range shift priority value looks like this. It's actually a very different curve. And this is also used elsewhere. And this was used in version 2.0 of Linkage Mapper. And so what we recommend is that actually as a starting point for any given landscape, you can have a curve that's a relative blend between the two. And I didn't point out very clearly that each assumption has its benefits, but also its costs, questionable assumptions. And so this is a way of meeting the best of both of those. At least that's the hypothesis. This is in the experimental phase. And so when you go ahead and map those linkages using the climate analog settings, you get a map that looks like this, where the lighter linkages are the higher priority. But if you look at range shift settings, you get a very different set of priorities, with the higher priority being the ones going from the really hot, dry areas to the really cool, wet areas. And so if you combine those two in that formula, you're able to get more of a balanced blend between both of those. And so really interested in finding other colleagues and practitioners that are wanting to dig into this further with me. We'll get into that in a minute. But first, let me summarize 2 of the 3 points here. First, with range shift climate gradients, each one of those different assumptions yields different priorities, but they're both part of the same equation. And it's context specific which one of those two you really are much more interested in. For instance, if you're in a mountainous region or not. And but as a linkage mapper user, you can balance between the two and find that proper balance. And then regarding the introduction to the linkage mapper software, I briefly overviewed 6 of the different toolboxes, tools in the toolbox, and how they can be combined.
Now, there are several different opportunities for you to engage at this point. One is you can get this presentation. You can email me for the slides or the recording, as long as there's not any sort of embargo on that through SCGIS. Otherwise, you can get it through SCGIS soon, I'm sure. You can also go to our GitHub site and try version 3.0 beta that I mentioned. And here's the URL spelled out. It also links to the white paper and technical specifications of this new feature. And the table is actually set for people to co-write either a journal article about this or improving the climate functionality, or simply to be a pilot region. So there's a lot of opportunities here to engage. And of course, we've got the Linkage Mapper community forum and our website. So hopefully we'll see you at one of those places. And I briefly want to acknowledge the many people involved in this project. No time for all these names here, but I wanted to at least give a big shout out and thanks to the software engineers, Darren Kavanaugh and Randall Green, that have been instrumental in this project. Darren is currently the lead engineer. And thank you to everybody else involved in this and our funders. And thank you for your attention. Thank you very much.